Mostly. So should have those for you guys next time. Um, so yeah, we just uh, test mostly great. I want to go over like one or two more things as I look through before I settle on um, final scores or whatnot. So far they've been the average, even with the standard curve I've been applying, is a little bit less than maybe I would have liked. So I might have I'm thinking on, Wednesday or Friday, giving like one other bonus question to just opportunity to steal a couple more points to tack on. Like I think like 5%-ish is what I'm looking at. Would just be volume problems. So that's what I'm thinking as of right now to plan on doing that. I have something sketched out. I need to like proofread it or whatever, but that's my thought. And so let's plan on like Friday if that's going to happen. That'll be a Friday thing. Seem okay? As Wednesday seems like a quick turnaround, especially if I'm telling you I'm not sure it's that I'm doing. I'm thinking we're going to do that. Yes. It could not hurt you. It would only be only to help. So I'll have by then we'll surely have everything finalized, and it'll just be I'll give you should be able to give you your stuff back on Wednesday. I'll enter in what your score is so far, and then we'll add the adjustment after the extra question or two when we do that on Friday, and it'll just can only get better. Sound okay? Okay. The other piece is that this is now we're entering in like the final phase of topics for the semester. So we need to do some work with differential equations, and I'm going to do a couple of other additional integration topics kind of sprinkled in at the same time. I'll try to be clear as to like what's AP topic and what I think is just like, hey, we should do this because in your first or second year calculus course you're going to do this, and it'll be nice to have seen it before. Topics, so we'll have some of both here in this last chapter. Everybody okay? Once we close this out, which I'm hoping would be like the endish of March, that'll leave us a lot of time to just do some like targeted review for the AP exam. So we'll probably be able to take full sections of practice testing class under like similar type of settings, talk about like things that we saw in these exams, all that kind of jazz. Everybody feel okay with the plan? Because I think, we have spring break, like the endish of April, and then we're back for like 2 days, and then you guys are gone. Something like that, or some weird, like there's a week left of school or something for you guys after we come back from spring break, which is like kind of terrible timing, but like whatever, it is what it is. So I will say this before we get just starting here. If your hope is to do well on the AP exam, right? If you're planning like this is something I want to do well because I know that I can get college credit out of this, and it's credit that I would like to have, because it's like $5,000 of free tuition or whatever, basically, for scoring well. You need to start thinking about preparation well in advance. This should not be I'll just look over stuff a couple days before. This should be like, I'm going to try to do like 2 hours a week for the 4 weeks like preceding the exam. So I'm not like cramming at the last minute, but I'm like slowly chipping away at like the stuff that we've done, so I feel really comfortable and confident and I can do things fast, so that I've remembered things and I've gone over it multiple times, so my memory's really sharp on it. That is the way to do well on this. It's not I'm going to do like 10 hours in a weekend and then take the exam and think that that's going to be the best way to do it. It's not. Okay. So I know when the seniors are done, brains kind of turn off and we have a tendency to like, I'm on a break time, which is fine. But if the plan is that you're really trying to do well here, I'm just trying to like make sure you've kind of thought this through and had a plan, so it doesn't feel like I'm springing this on you at the last minute. I want to talk about it now so we can start thinking about it now. But that's the way to do well. You don't want to spend 20 hours in a weekend studying. You want to spend 20 hours over the previous month doing stuff and doing it over and over and over again, so that you feel really sharp and well practiced and you know what to do when you see it, and you can do it fast when you see it. You know what I'm saying? Okay. Cool. I'm not trying to scare you or dissuade you. I just want to be just being realistic, just being realistic. All right. So our final major topic, as far as the AP is concerned, is dealing with differential equations. Now, we are just going to dip our littlest of toes into the topic of differential equations. You could take multiple courses as a college student or as a math major or whatever, dealing with techniques for solving differential equations, and it's a very deep field of study. We're just going to kind of get a little tiny introduction here and look at some basic techniques for dealing with these things, but that's the main focus here for the next test. We'll be dealing with these differential equations. In addition, like I had said before, I will sprinkle in some other integration techniques or integration topics as we go that I feel like are things that we should probably see. All right. So the usual place where we start talking about a differential equation is talking about something like modeling population. So if you want to talk about modeling population growth, that's like a two-variable system in the simplest way of thinking about it, where you have time and population. Right? Which one of those would be the independent variable? Time, and population would be the dependent variable, right? Your population growth should depend on how old the population is and how long they've had to reproduce, right? So our most basic model would be to assume that population grows at a rate proportional to the size of the population. Now think about what that's saying. Why would population grow proportional to the size of the population? If you assume the rate of reproduction is constant, right, then it should just be a constant multiple of population, right? If 1 in 10, if the birth rate is 10%, if you have 100 people, you'd expect 110 offspring over, like that time interval. Everybody feel okay with that idea? So seems fairly reasonable. If we do that, then we'd say that the dp/dt, the rate of population change with respect to time, should be k times p, some constant times the population. Does everybody feel okay with that basic set of assumptions there? Now, we're going to assume that the population is non-zero and P of t is greater than 0 for all t. Why would we want to make that assumption? Well, P of t greater than 0. Well, your population may not always be increasing, right? But what would you say about the rate of population if you had 0 people, or population growth if you had 0 people in your population? Can it grow? Can you have negative people in a population? Does that make any kind of sense at all? No. Now, your rate of growth could be negative. That's fair, and we've seen that. We can see that in biological systems. We can see that in human history. Like in the Middle Ages when the plague was going on, the rate of population growth was surely negative, particularly in Europe where they were hit the hardest. Or if you look at the native populations in the Americas post-Columbian exchange, certainly had a negative rate of population growth as they were, again, wiped out by disease and, like conquistadors and all kinds of other factors. Okay. So if k is greater than 0, then the dp dt should also be greater than 0. Why can we say that? Because we've just assumed that the population is always greater than 0, so k times p should always be greater than 0, right? Okay, this would imply that population is always increasing, and furthermore, as p of t increases, so does p prime of t, or dp dt. Does that feel okay? All right. So we're thinking about, okay, we have a function p of t, and the more that increases, so does its derivative. Can you think of a function whose derivative is a constant multiple of itself? E to the x is the idea there, yes. So k times e to the x, the derivative of that is still k times e to the x, right? Everybody okay there? So if we consider all possible solutions to the differential equation dp dt equals kp, it's a differential equation because one of the variables is a derivative, right? dp dt is a derivative. That's one of our variables, the rate of population growth. We have that, like a set of functions that looks like that, right? Is everybody okay there? Right, those all look like exponential curves, just with a different factor of k being multiplied out front. But we said we can have only positive values, and we know that the time has to be positive. So our possible solutions kind of reduce down to just things in the first quadrant. All right, because we said population has to be positive, and time certainly has to be positive. So let's think for a moment under the kinds of conditions in which this sort of model would be appropriate for population. So under ideal conditions, this is probably an accurate description. By ideal conditions, we mean like an unlimited environment, so space isn't an issue, adequate food supply, absence of predators, immunity from disease, etc. Now, in reality, any or all of these become limiting factors as populations grow. In practice, we'll call the upper bound on a population its carrying capacity, and we'll use the letter M to represent that carrying capacity. So when the population is relatively small, the ideal conditions model will still be appropriate. But if it, like the population gets larger and larger and larger, we should probably see the growth rate tailing off as resources become scarcer, or, like disease becomes more prevalent, the denser your population becomes, diseases transfer much faster. So let's look at a second model that maybe gives us a little bit better description of what's going on in reality, where we can incorporate this idea of there being some upper limit, some carrying capacity for a population. Does everybody feel okay so far? We're just kind of telling a story. So we have that if dp dt can equal kp when p is small, right? Initially, that seems fine. Like if the resources are in excess, that might as well be pretty close to unlimited. And then we need the rate of population growth to become negative if the population exceeds the carrying capacity, right? Like if we get too many population, we need it to shrink back down and start dying off so that we end up underneath that carrying capacity. Is everybody okay with that idea? So if we incorporate both of these assumptions, we're going to end up at the differential equation dp dt equals kp times 1 minus p over m. So let's see, why does this model incorporate these assumptions? When p of t equals 0, that'd be early stages, right? I'd have 0 over p minus m, which would just turn into 1. So I'm ending up with like k times p. Everybody okay there? What happens when the population is equal to m? Well, m over m is 1. 1 minus 1 is 0. 0 times kp is 0. So that would be no population growth, which is what should happen if our population is at the carrying capacity, right? We should have no growth. It should just hold steady. Everybody okay there? We call, when p of t is 0, this is 0 too, so just 0 times 0. I'm done. So that's equals 0. So when the differential equation is equal to 0, when the rate of change is 0, we call those equilibrium solutions. So those are the values for p that make dp dt 0. So the equilibrium solution will always be in terms of like the independent or the dependent variable, here the p. What happens if p of t is between 0 and m? Well, then this fraction is less than 1, and 1 minus something less than 1 is still positive, so we're going to have a positive growth rate. And as p gets closer to m, that's going to become closer and closer to 1, so this 1 minus something is going to become a smaller and smaller number, which is going to shrink this growth rate because you're multiplying by a number less than 1. And the closer p gets to m, the closer 1 minus p over m gets to 0, which is doing what we want it to. If p is greater than m, what's going to happen? Well, then this number, p over m, is going to be bigger than 1. 1 minus a number bigger than 1 is negative. That'll give us the negative growth rate that we want when we exceed the carrying capacity. So this seems like it represents all the features that we want our population model to actually behave like, right? Does that feel okay? All right. So if we sketch a graph of this solution, or possible solutions, we have our two equilibrium solutions where the graph acts like, where those equilibrium solutions act like an asymptote for our graph. So if we're before, we're going to be dropping down towards that equilibrium solution. If we're below, we're going to be rising up towards that equilibrium solution. But we're really never going to cross those equilibrium solutions. Okay, so that's just kind of an example of us building a differential equation model. Let's talk about, like, in practice, what would you be responsible for doing and what would this look like for you guys, because it's not going to be, here's a real world situation, build a differential equation to describe this, because that's beyond the scope of what you're capable of right now. Now, you know, way further down the line in a different class, in a different setting, would that be realistic? Sure, but not now. Everybody's okay? So let's just kind of start with some basic definitions and talk through on kind of how to deal with this sort of thing in practice. So we say a differential equation is an equation that contains an unknown function and one or more of its derivatives. So for example, y prime equals x times y. Y prime is the derivative of y. Y prime is a function of x and y. We say the order of a differential equation is the order of the highest derivative that occurs in the equation. So this would be an example of a first order differential equation because the biggest derivative is a first derivative. Bless you. If this was y double prime equals xy, it would be a second order differential equation. Everybody's okay with that nomenclature? We say a function f is a solution to a differential equation if the equation is satisfied when y equals f of x. So for example, we say y equals f of x is a solution to y prime equals xy if the derivative of f is equal to x times f of x. Right? If y equals f of x, then the derivative of y is the derivative of f of x, and y is f of x. Everybody's okay with that? To solve a differential equation, we're expected to find all possible solutions of the equation. But we've already really kind of done this, right? So for example, if y prime is equal to x cubed, and I want to find all solutions to this differential equation, well, I just find the general antiderivative of y prime. So it would be x to the fourth over 4 plus c. Everybody's okay? It's like, oh, Mr. Kulik, maybe this won't be so hard. And I was kind of scared at the beginning when we did all this population mumbo-jumbo talk. But when you just did this as an example of solving a differential equation, I'm like, I can do the heck out of that. So one very familiar type of problem you'll be asked to do right now is to show that is these show problems. So this problem says show that every member of the family of functions y equals yada 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 is a solution to the differential equation y prime equals 1/2 y squared minus 1. So to do this kind of a problem, we have two routes that we could go. We can try to take this and find y prime, or you could start at y prime and try to integrate back to get to this y. Which one do you feel like looks easier? No way, man. You should be doing the differentiation. Remember, integration in general is harder than differentiation, right? Because I'm looking at that exponential function. I have no idea how to integrate that. Because a u sub will not be, I don't think is going to do it for us. Okay? So let's start with the y equals, and we'll differentiate that. To differentiate that, what are we going to have to use? Quotient rule. So the quotient rule is the denominator times the derivative of the numerator. What's the derivative of the numerator? C e to the t, and then minus the numerator times the derivative of the denominator, which would be negative c e to the t, over the denominator squared. Is everybody okay with what we've done here? So what I would do is I would notice that each term in the numerator contains a c e to the t. So I'd factor that out front. And now this negative and that negative are going to cancel each other out, right? Everybody feel okay there? So when I combine my like terms, I'm going to have 2c e to the t over 1 minus c e to the t squared. So this guy can be my y prime, right? Okay, just don't know what I'm doing here. And remember that we have that y prime is equal to 1/2 y squared minus 1. And we know y, we're given that as well. So I just need to check to make sure these two sides are going to be equal, right? So to do that, I'm going to FOIL out the numerator, but I'm not going to do the FOIL out the denominator. Why would I not want to FOIL out the denominator? Because it looks like I've already got what I need there, right? Everybody see that? Now, what am I going to do with this minus 1? What do we think? Common denominator, very good. What would the common denominator be? Yeah, 1 minus c e to the t squared, right? I'll go ahead and FOIL the numerator out. And then let's see here. Those guys subtract to give us 0. These guys subtract to give us 0. But this minus makes that a positive. So I add those together. And then, and there we go. Now, eventually we'll be doing integration to solve these differential equations, but here we're given the solution. We just needed to check it. The best way to check the solution is differentiation. The integration could be real bad. Okay? Like beyond the scope of what you're capable of doing bad. Everybody's okay? So this becomes mostly an exercise in like algebra and trying to not let it get too yucky, you know. But whenever they give you a show problem, they are right. Those are the solutions. It's just a question of like, can you jump through the algebraic hoops to get the two things to match up the right way? Okay, so it says find a solution of the differential equation y prime equals 1/2 y squared minus 1 that satisfies the initial condition that y of 0 is equal to 2. So we know the solution for this. It was given to us in the previous problem, right? So if I know y of 0 is equal to 2, I can plug 2 in for y and 0 in for t and try to solve for c, to find the specific c that's going to give me that particular solution. Now, e to the 0 is just 1, right? So those just kind of cancel out. How would I solve this equation for c? I have 1 plus c over 1 minus c is equal to 2. Yeah, multiply both sides by 1 minus c. Or you could think about this as a cross multiplication problem. Either way of writing that is appropriate, or either way of thinking about it would be appropriate. And then we just kind of distribute things through, and we can subtract 1 from both sides and add 2c to both sides. And if I divide by 3, I get c as 1/3. Now, who likes the way this looks? Hopefully none of you say, oh yes, please, I love fractions inside of fractions, right? Now, is this answer correct? Yes. Would I mark it as correct? Yes. Would this be what it looks like on a multiple choice question? No. What are they going to do? It's just going to multiply the top and bottom by 3 to get rid of the fraction inside of the fraction. So if you checked in the back of the book, assuredly that's the way they would write the answer, not with the 1/3 in there. Is it still right? Yes. But like anything else, it's just a matter of like style on how far simplified do we want something. If it's a non-calculator time test setting free response style question, the simplification does not matter. If it's multiple choice, obviously, like, it's got to match what's in the multiple choice question. But if you have to provide your own answer, I don't really care about the simplification, as has been kind of the story the whole way through, right? That's always kind of been our standard. Agreed? Okay. So those are really the two style of problems you're going to encounter in 9.1. Is going to be show that this is a solution, or given the solution and a specific value, can you find the specific solution, right? Can I take that general solution with the C in it and then solve for the specific value, which should be fairly easy, right? These are things that we've already kind of done before. Any questions about what I've done so far? Does this feel okay? We're going to look at 9.2 also then. So in 9.2, we're going to talk about slope fields, or they're sometimes called direction fields, depending on the textbook. So let's say we wanted to sketch the graph for the differential equation, y prime equals x plus y, where y of 0 is equal to 1. How can we graph the equation for some function f of x, our solution, if we don't have the formula for f of x? Right? What are we going to do? Well, we know that the slope of a solution to that function will be the sum of the coordinates. That's from the differential equation here, right? The slope is x plus y. Everybody's okay with that? So that means that at the point, say, 2, -1, the slope would be 1. So what if we just graph a tiny portion of line that passes through 2, 1 as a line with a slope 1? We can then graph one tiny part of a possible solution graph for the differential equation y prime equals x plus y. Everybody's okay with that idea? And if I do that for many points, I can create what's called a direction field or a slope field. Everybody okay with how I've generated this picture? I've taken out like the grunt work of doing it, because I think it's a huge waste of your time to just sit here and be like adding up x and y coordinates and sketching in something with the appropriate slope. Now, if we add in the initial condition, y of 0 is equal to 1, that'd be like this point here. So what I'm going to do is I'm just going to kind of use my direction field or my slope field to kind of sketch in what f of x might look like. What do you guys think? You see how I use the slope field to do that? I'm just kind of using my eyeballs here. I'm not doing any mathematics. Just kind of looking at the way the slope fields, or it's like a current in a water or whatever. If I just drop this in, where's it going to kind of be pushed to? Is that a decent analogy there? You can kind of see it. And look, there's the actual function, which looks pretty close to what we sketched, right? All right, let's do another example. It says sketch the direction field for the differential equation y prime equals x squared plus y squared minus 1, and then use part A to sketch the solution curve that passes through the origin. So this is my chart of kind of how I went about doing this. So I just made like, a column for X and Y's. And then I did the calculation underneath it. So notice I took the X's, the only X's I considered were from like -2 to +2. And then I kept one Y, and then I'll do -2 to +2 with a new Y, and over again. And it's going to take a million years, and it's really tedious. And I won't ask you to do it by hand on a test or a quiz, because like, who has time for that? It's going to take a half an hour to do that. And it's like, you have better things to do. I have better things to ask you to do than like a bunch of computation to create a slope field. I'll just give you the picture. So here's our picture, right? It says the solution is at the origin. So there's my picture, or my solution at the origin. What is it going to follow from there? Well, it looks like it would do something like this. You guys buy that? That's it. You did it. You sketched a solution. It's like, I feel good, Mr. Kulak. I like this. Yeah, that's lost to something else. I don't. Yes, AJ. Sure. All right. Next up in this section, we're going to talk about a technique called Euler's method. Euler's method is used to approximate solutions to differential equations. So let's say we have y prime is equal to x plus y, that same differential equation we had before, and then y of 0 is equal to 1. So the idea here is we can use this information to write a linear approximation. Remember, we did that in first semester. So that linear approximation has slope 1, and it's passing through the point 0, 1. So if I write my point slope, I have m times x minus x1 plus y1, right? So I have x plus y. So I go ahead and I graph, that's the blue, that linear approximation. So using that linear approximation, we can approximate a new point on the solution curve by moving some distance left or right. We call this distance the step size. So suppose we pick the step size to be a half a unit. So I've moved a half a unit to the right. And we can find then the new approximate y-coordinate by using that linear approximation we made before. So if I plug in 0.5 to x plus 1, I'd have 1.5. So that's like my new y-coordinate. So that's there. And now I can find a new slope using my differential equation. So the slope at this new point is going to be 0.5 plus 1.5. So that slope is 2. And now I can make a new linear approximation doing that and continue to like build this process indefinitely, right? So what I basically am doing is I'm creating a piecewise linear function that approximates the solution to this differential equation, right? Instead of it being a smooth curve, it's just going to be like little linear chunks that's going to have approximately, or follow the approximate path of this. Does that feel okay? So what's going to happen to this as the step size decreases? Are we going to get a better or worse approximation? Better, right? What happens when the step size becomes infinitely small? It's exactly the solution, right? If the step size becomes infinitely small, you have the exact solution function. So here is the general formula for the Euler's method. Let's do this with our calculator, though, and let me show you how we can kind of automate this process. So it says use Euler's method with step size 0.1 to construct a table of approximate values for the solution of the initial value problem, yada, yada, yada. So we know we have 0 and 1 to start. Right? My first x-coordinate is going to be 0 plus 0.1. My next x-coordinate is going to be 0.1 plus 0.1, and then 0.2 plus 0.1, and so on. Everybody's okay with that? So like 0.4, 5, 6. Is everybody good at how I filled in my x-coordinates? All right, so I'm going to enter in the initial value for y. I'm going to do my initial value for y. And then I'll have plus the slope. What is the slope? So I'm going to write it as the slope is x plus y, right? So I'm going to write it as 0 for right now plus my y value, which I'm going to do as ands. Is everybody okay there? So press enter. Oh my goodness. I'm so dumb. We already have it at 0. We're at 0.1, guys. Ugh. All right, so 1, and then ands plus slope, which is 0.1 plus the old y value. Sorry here. Oh yeah, okay. Creepers. All right. Go back and look at my formula. H is my step size. That's the 0.1. and then times 0 plus ants, the previous y value. There we go. So that's my new y. I'll update this. So now my previous y was this one, which is 0.1. So I'm just going to update that to be 0.1. I get 1.22. That's my next y value. Then I'll update this to be 0.2. And I'll just kind of continue kind of cranking through this. Does that feel okay there on what I'm doing? I'm just kind of incrementing along, getting my new y coordinate each time. So if I wanted to, I could plot these x, y's. What do you guys think? Do you understand what I'm doing on the calculator or no? I'm going to take your silence as you're okay with what we did. Worst case scenario, you can just kind of do it manually, but that's the gist of this section. Okay, so drawing sketching solutions on the field or on the direction field or slope field with different starting conditions should be relatively easy. You guys seemed like you felt real good about this. Yes?
So those, like, you just find the point and then you fix it.
Yeah. There's nothing more to do than that. So same idea here on number 2. The trickier one, are these going to be match the differential equation with its slope field? So those can be a little bit challenging. So my suggestion for these ones is I want to think about where the equilibrium values are and then do some like little test points. So for example, if I look at the first equation, it's really annoying that they're in different parts, is 2 minus y. So when y equals 2, the slope should be 0, right? Everybody agree with that? So I'm going to look for one of these slope fields where when y equals 2, I have the slope field is flat. That looks like this one here, right? Okay. So that one turned out to be pretty easy. Ooh. But it could be this one too, right? Both of these have equilibrium values at y equals 2. Let's be a little bit more careful here. So this one could be x equals 0 or y equals 2 for my oh my god, stop. All right. This one doesn't have a constant equilibrium value, right? But like x equals 0 and y equals 1, or y equals 1 and x equals 0, like all those would give you zeros, right? But it's not going to be a constant equilibrium value. Here, um, sine is 0 at 0 and every pi units after that, right? So let's go through and look here now. So this one I know is number, what is it? It's 4, 5, 6. Nope, it's 3. 4, 5, 6 are the numbers. Gosh, dang it. Stop being so stupid. So this one's got to be 3. Because if I look, well, we got to tell the difference between 3 and 4 on these, right? Because those are the only ones. So the y, we have the y equals 2, right? What's the difference between 3 and 4? 4 also had x equals 0. If I look at x equals 0 here, notice that those are flat. So this one is 4, this one is 3. You guys see the difference? If I look at all the slopes along x equals 0, they're all horizontal. You guys see that? Okay. So this one, we're looking at, well, what do I notice here? This is kind of interesting to me, right? That's the line y equals x, right? And the slope there appears to be 1. So when y equals x, I'm sorry, that should be y equals negative x, right? Because it's got a negative slope to it. If y equals negative x, we should be negative 1. That certainly appears to be 5. And if I look at the last one, then by elimination, that should be 6. But I feel pretty good because look, 1, 2, 3. I got a flat one, a little after 3, and a little after negative 3, and then a flat at 0. So that looks like pi, negative pi, and pi. That all looks good to me also. So these typically are the most challenging ones. Usually the equilibrium values are going to be what you want to use to pick out which one is which. Does that make sense to you guys as to what I was kind of looking at to figure that out? Again, you don't want to build the slope field by hand. That's stupid, although effective, really time consuming, right? Nobody's got time for that nonsense. All right. That feels like enough for today, right? So we just kind of dipped our toes in. We'll look at next class. We're going to look at methods for solving these differential equations by hand, like using integration. That'll be next time. And then I think we'll do some integration technique stuff on Friday, some additional integration technique stuff. So we'll talk about integration by parts and maybe either trigonometric. Maybe we'll do both trigonometric and trigonometric substitution. So the idea for that would be, like if you look at the inside cover of your text or the back cover of your textbook. Let's see here. So like all these tables of integrals that involve like these square roots of like a difference of two squares are all like real obvious, or the sum of two squares are all real obvious candidates for trigonometric substitutions. We'll talk about kind of how to do that. But a lot of times they'll just be presented as like, use the formula, but how did you get these formulas? And this is a common topic in your first or second year calculus course that you would spend some time doing as one of your core integration techniques, along with U sub and integration by parts and I'm trying to think, or the partial fraction decomposition that we did already. So we'll look at some of that stuff next time. What do you guys think? It's like, yes, Mr. Glick, please stop talking. My brain hurts. Yes.
So the two sections we did there, are those on the AP test?
Yes. Yes. So like, surely you'll get multiple choice questions where it's like, here's a direction or slope field, like which differential equation is represented by this, or here's a differential equation which slope field matches or describes the solution set for it. Very common AP question for you guys. Would not be building a slope field, although I see people like make those questions and put them into the MyAP. I don't think that they would ask you to make a slope field. I've never seen a practice question from the AP site that asks you to make your own slope field. It's always just like using it to do something. Or like, here's a slope field, like draw in the solution with this initial starting condition or whatever. Like those are super doable, super common questions. Paulo?
For the AP test, are the multiple choice questions online? Do you know?
I don't think so. I think you're still doing them by hand. That's the way they were the last 2 years anyways. I haven't heard that they're moving to do it electronically yet. Is that... anyways, anybody else with questions about stuff? And again, I'll advertise when we're doing something that's not directly AP. So like when we do integration by parts, that's a BC topic. You know, the trigonometric substitution's a BC topic. I think technically the partial fraction decomposition might be a BC topic. I'd have to look that up, though. I can't remember. We'll do, in this differential equation, we'll look at one technique. For linear differential equations, that's a BC topic, as opposed to the separable, which is squarely an AB topic. And then we'll do some like improper integrals also. That'll be the last integration topic. Additional one that I think I would want to do. And that's a BC topic also. So there's not a lot of AB stuff left. We did good this year, kind of blazing through stuff.